This is a video presentation of the ProsoDeep project, focused on deep understanding and modeling of the hierarchical structure of prosody. My name is Branislav Gerazov. I come from the Faculty of Electrical Engineering and Information Technologies in Skopje, Macedonia. I worked on this project with my scientific supervisor, Gerard Bailly, from Gypsy Lab, Grenoble, France, and Yi Shu from the University College London, and Phil Gardner from the EDUB Research Institute. First, I would like to acknowledge that this project has received funding from the European Union's Horizon 2020 Research and Innovation Program under the Maria Skłodowska-Curie Grant Agreement number 745800. This is an outline of this video presentation. I will start with an introduction to the topic and the motivation. I will talk about the objectives of the project, and then I will go over the models we developed within ProsoDeep, which are the PySFC, the weighted SFC, the Variational Prosody Model, and the Variational Recurrent Prosody Model. At the end, I will talk about the database that we recorded. Speech prosody is a multidimensional phenomenon comprising intonation, energy, and rhythm. It is the carrier of linguistic information, such as sentence structure, focus and contrast, lexical stress, paralinguistic information, such as attitude, intention, style, and non-linguistic information, such as gender, age, personality, and emotions. To illustrate this complex phenomenon, here we have an example French sentence, les gamins coupés des rondins, which has been segmented and annotated using PROD. Concerning the multiple dimensions in which prosody resides, we can see the change in amplitude or the change in intensity in the speech signal in the top plot. On the second plot, we can see with the blue line the pitch contour or the intonation of this utterance. The rhythm of the utterance we can see with the lengths of each of these phones within the sentence. On the lower half of these annotations are the layers that represent information that is passed on using prosody. The first layer of these is the attitude layer or the phrase layer, so we can see that this sentence is a declaration. On the following two layers are the left dependency and the right dependency contours, which illustrate the syntax of the sentence. So basically, the subject of the sentence and the verb phrase, that's left dependency, or the verb and the object, which is right dependency. Finally, we have the morphological layer of information, in which le and de are marked as clitics. All of this information is embedded in the prosody signals that we discussed at the beginning. In recent years, prosodic research has considerably enlarged the spectrum of properties and functions. Audiovisual prosody, for example, analyzes the impact of coverbal signals, such as visual displays and body movements. In contrast, prosodic models able to map signals to functions are rare. Comprehensive models of rhythm and intonation have difficulties coping with this expanding dimensionality. And machine learning techniques, which are state-of-the-art at the moment, do not offer any structuring principles. Most state-of-the-art prosody models are in fact intonation models, and they follow a bottom-up approach. That is, from signals to functions. One example is the generalized command-response model that we developed with Phil Gardner, Pierre-Edouard Onnet, and Alexander Joreski. This model can give a good parameterized reconstruction of the pitch contour. Here we see an example sentence whose pitch is decomposed into one phrase atom, this faint red line, and multiple local accent atoms, which together with the phrase atom can give a fairly good reconstruction of the pitch contour, especially in the voice regions which are marked with green. The main problem with the bottom-up approach is that it's difficult to establish the linguistic significance of the extracted model parameters. In other words, how do we connect the atoms that are extracted by this generalized command-response model to the linguistic functions that are encoded in the prosody? There are state-of-the-art prosody models that take the opposite approach, going top-down from linguistic functions to prosodic contours. One example is the superposition of functional contours model, or the SFC model, which decomposes prosody into functionally relevant elementary contours, taking the annotated linguistic functions and trying to figure out what is their prosodic encoding, and superimposing them to get the prosody that is in the signal. The main problem with the SFC model is that it learns only the average contours for each encoded function, and thus gives a poor reconstruction. This also limits its application to speech synthesis as well as prosody analysis. In the current era of dominance of deep learning, state-of-the-art speech synthesis systems are based on machine learning prosody models, decision trees, and recurrent neural networks. They can handle big amounts of training data and give natural-sounding prosody from the textual input. However, there are two main problems in using these models. They are susceptible to the averaging effect, which results in lack of variation in their output. And the second is that they are a black box model that gives no insight into the structure of prosody. Within ProsoDeep, we wanted to offer solutions to these problems in the field of prosody modeling. Thus, the prime objective of ProsoDeep is twofold: to delve into the structure of prosody by using the strengths of the top-down and machine learning approaches, and two, to design a deep prosody model that will be a merge between these opposing paradigms. At the start of the ProsoDeep project, I implemented the SFC model in the Python scientific ecosystem. This is a schematic of the SFC model, in which the contour generators are the core. These are trained based on the prosodic skeleton and the metalinguistic functions that were labeled in the data, and then can generate contours which are overlapped and added to synthesize again the prosody. Here we see a schematic diagram of the contour generators used in the SFC model. They are based on shallow neural networks which receive the rhythmic unit position as input and output the functional prosodic contour. They are trained within an analysis by synthesis loop illustrated here. Here we can see how a trained contour generator can be used to generate a prosodic contour. First, we encode each rhythmic unit within the function scope with positional information. This positional encoding is what gets passed as input to the neural network, which generates prosodic parameters for that rhythmic unit. The prosodic parameters generated in the SFC are 3 targets for the pitch within the vowel nucleus of the rhythmic unit, and 1 durational coefficient which signifies the amount of expansion or compression of the duration of the whole rhythmic unit. You can see that the contour generators generate this functional contour 1 rhythmic unit at a time. This functional contour has 2 subscopes. Let's say it's a left dependency. So we have a left subscope, an anchor point, and then the right subscope. And this affects the way each unit is encoded in the positional ramps. Once trained, the contour generators in the SFC model can decompose a pitch contour into the elementary or prototype contours for each of the linguistic functions for that utterance. Here we don't show the duration coefficients, but the decomposition is equivalent to this one. With the trained SFC contour generators, we can see how the prosodic contour changes with the length of the scope of the functions. In these expansion plots, we see how the prosodic contours of the different attitudes in our French data change with the length of the scope of these functions. The attitudes that we see here are the declaration or the assertion attitude, the question, the incredulous question, and the obviousness. We can also visualize how the prosodic contour changes for a function with 2 subscopes, here the left dependency functional contours. The numbers next to each of these contours give the number of occurrences of this particular scope length within the data. We can see in the top right corner here that the contour generator can efficiently extrapolate for scope lengths that it hasn't seen in the data. The implementation of the SFC model in Python is available within the PySFC prosody analysis system on GitHub as free software. We can see here in the lines of code that the SFC, which is implemented within the module SFC Learn, is only a tiny part of this whole system, which includes modules for dealing with data, for building the corpus, parameter setting modules, as well as plotting tools that give a fully functional standalone prosody analysis module. The PySFC prosody analysis system, based around the SFC implementation in Python, has been documented in a scientific paper that was published at the International Conference on Speech Prosody in 2018. We also used the PySFC to examine how the scope of the tone contours influences the modeling performance. Here we can see how the tones look if we only have a single rhythmic unit in the scope, And here we can see how they look when we add the preceding and the following syllable. What our results showed is that adding the following syllable increased performance in a statistically significant manner. In this way, we use the PySFC to validate a well-established phenomena in literature known as the carryover effect in Chinese tones. We published these results at the International Symposium on Tonal Aspects of Language in Berlin, Germany. We first improved the SFC by adding a weighting module to the contour generators to model prominence. We can see the weighting module here on the contour generator that was used in the weighted SFC. We call this the weighted contour generator. The weighting submodule receives the context of the contour as input. This is basically a one-hot encoding of the coinciding contours to the current one. It outputs, based on this contour context, a weight that scales the functional prosodic contour output by the regular contour generator. Here we can see results of decomposition using the weighted SFC for a declaration and an incredulous question. We can see next to each of these contours a weighting factor output by the weighted SFC. What we can notice between these two example utterances is that the syntactic contours, which are the left dependency and the right dependency, as well as the clitic contours, have a diminished amplitude when elicited in an incredulous question compared to a declaration. Thus, using the weighted SFC, we capture the impact of attitude on contour prominence. This plot shows the distribution of weights for two different functional contours, the XX, which encodes clitics, and the DG, which encodes left dependency. We can see that the weights of these contours are only full-blown when elicited in a declaration or an exclamation attitude, while for the other attitudes we have a suppression of their amplitude. This allowed the weighted SFC, when compared to the SFC, to capture the true prominence of the contours. For example, in the declaration attitude, we can see that the weighted SFC gave a very prominent clitic contour, but the SFC shows a diminished clitic contour. This is because the SFC captures the average XX contour, so the average clitic contour, for all the attitudes, while the weighted SFC can capture the contour per attitude, at least the weight of the contour per attitude. Here we can see that the weighted SFC also successfully captures the influence of emphasis or focus on the tonal contours. We can see that the tonal contour for tone 4 here, which occurs on the emphasized syllable, zhao li, on the li, is more prominent than the other tone 4 contours around it. Here we can see the impact of emphasis on prominence for the Chinese tonal contours for all the data. We can see that for the 4 tones, we have high prominence only when the tonal contour appears on the emphasized syllable. We published the weighted SFC and its results at the flagship conference Interspeech in Hyderabad, India. The Variational Prosody Model is the end result of our work in the ProsoDeep project. It builds on top of the SFC paradigm and introduces variational encoding contour generators, shown here in the figure. The variational contour generator is composed of a variational encoder and a variational decoder. The encoder receives as input the rhythmic unit position and the contour context, much like the weighted SFC or the weighted contour generator here, and then encodes them into a prosodic latent space that can be sampled and then decoded into a functional prosodic contour. Another improvement of the Variational Prosody Model is that it introduces a unified network architecture which jointly optimizes all of the contour generators using backpropagation. This is more efficient than the analysis by synthesis loop used in the SFC and the weighted SFC. We first wanted to see if the Variational Prosody Model is capable of capturing the prominence that we could capture with the targeted submodule in the weighted contour generators. Here we have a plot of the latent space of the clitic contour XX for the different attitude contexts. We can see that for the declaration and the exclamation, indeed we have a full-blown contour or a prominent contour, while for the other attitudes we have a diminished or less prominent contour. And in fact, we can see that the Variational Prosody model within this latent space captured a prominence vector that we modeled specifically with the weighting submodule of the weighted SFC. We also wanted to confirm if the Variational Prosody model can capture the impact of emphasis on prominence that we captured with the weighted SFC. Here we see the prosodic latent space of tone 3, which is the low tone in Chinese. We can see that the Variational Prosody model has successfully captured high prominence on emphasis and lower prominence when not on emphasis. This corresponds to our findings with the weighted SFC. However, what the Variational Prosody model also captured is a difference in shape when the tone precedes emphasis. So, when a tone 3 precedes an emphasized tone 3, it turns into a rising tone instead of a falling tone, which is tone 2, and this is basically tonal sandy, which was successfully captured by the VPM in the data. To confirm that the Variational Prosody model enables capturing of variance beyond amplitude scaling, we did a principal component analysis of target estimates obtained with the analysis by synthesis loop in the SFC, here shown for tone 4, and the generated tonal shapes for tone 4 using the Variational Prosody model on the bottom row. And we can see here that the first component is basically the amplitude scaling, while the second component is the tilt or the slope of the contour. And we can see that the VPM actually captured part of this variation in the tilt or in the slope of the contour. The final stage of the development of the Variational Prosody model was the adding of recurrent neural networks within the contour generators. This allowed for decoupling of the prosodic latent space from the length of the contour. Here we see a schematic diagram of the variational recurrent contour generators. Similar to the variational contour generators previously introduced in the Variational Prosody model, we have a variational encoder that receives the contour context, but this time not the rhythmic unit position. It maps this contour context into a prosodic latent space, which can then be sampled and decoded, and fed into a recurrent neural network made up of LSTM cells, which then outputs one rhythmic unit position at a time through the contour decoder, the functional prosodic contour. The decoupling of the contour context from the length of the function scope allows us to model longer functions using this model. For example, here we have the prosodic latent space for the left dependency function mapped out by the Variational Prosody model without the recurrence. We can see that the prosodic latent space is not easy to understand and to analyze. By using the recurrent neural networks within the contour generators of the Variational Prosody model, we get a prosodic latent space that is easier to read and interpret. Here we have the left dependency again, conditioned on the attitude it appears in, but not on its length. We can see that for declaration and exclamation we have a more pronounced contour, while the prominence of the left dependency contour diminishes for the other attitudes, as was determined with the weighted SFC. A short summary of all the models developed within the ProsoDeep model was submitted at the workshop on prosody and meaning in Aix-en-Provence in France. We are also currently working on a journal submission that will give all the details behind the Variational Prosody model. All of the presented models have been integrated into the ProsoDeep prosody analysis system and have been made available as free software on GitHub. If we compare the number of lines of code between the ProsoDeep system and the PySFC system, we can see that most of the work during the ProsoDeep project went into the learning module and the models module, which implements the Variational Prosody model. Another important part of the work done in the ProsoDeep project is the recording of a prosodically rich database. Towards this end, I developed a prompts generation package in Python, which is language independent, and which I use to analyze Wikipedia articles in the target languages. The package implements grapheme to phoneme conversion based on dictionaries such as Wiktionaries for English, German, Vietnamese, and French, and I also implemented rule-based approaches for Chinese and Macedonian. The package implements a prompt selection algorithm based on a const function and greedy prompt selection. At the end, prompts were manually pruned. The prompts generation package has also been made available as free software on GitHub. The final database includes prompts in English, German, Chinese, Vietnamese, Macedonian, and French, with around 700 utterances and 11 attitudes for each. I would like to give a big thanks to Coriander Villon for helping me record the database and to all the speakers that participated. Upon completion of the segmentation and annotation of the data, the whole database will be made available on the Zenodo server as open access. At the end, I would like to point you to the ProsoDeep website, which contains all the information about the ProsoDeep project, details on the ProsoDeep models, as well as links to the code and publications. With this, we end this video presentation of the ProsoDeep project. Thank you.